Hey everyone, Resin here. When making a transaction on an EVM chain such as Ethereum, you need to specify three key parameters: gas limit, max fee per gas, and max priority fee per gas. These parameters are crucial for determining transaction costs and priority. In this video, we'll explore how to efficiently calculate these values using Viem and Wagmi libraries. You can experiment with a live demo and review the complete source code. Let's explore a practical implementation of gas fee calculation by building a simple web page. We'll create a user interface that displays different components of the gas fee and analyze the code step by step to understand the underlying mechanics. Since the max fee component combines all fee components into a final value, we'll examine it last. Let's start by understanding the max priority fee per gas parameter, which is a crucial part of the overall transaction fee structure. Max priority fee per gas, often referred to as the priority fee, is the extra tip users include in their transactions to incentivize miners to process them faster. Unlike the base fee, which is determined by the network to reflect current demand, the max priority fee per gas is set by the user to ensure quicker transaction confirmations, especially during periods of high congestion. In most Web3 applications, when initiating a transaction, users are presented with priority options for their transaction fees. This feature allows users to strategically choose between lower fees for non-urgent transactions and higher fees when faster confirmation is needed. The priority selection directly influences the max priority fee per gas parameter, giving users control over their transaction costs and confirmation speed. To determine the max priority fee per gas value, we analyze the historical priority fees paid by users in the last 10 blocks. This approach gives us a reliable estimate based on recent network activity. We fetch this data using Wagmi's use fee history hook, which retrieves fee information for different priority levels: low, medium, and high. Each priority level corresponds to a specific percentile of fees paid, with the 10th percentile for low priority, the 50th for medium, and the 90th for high. This statistical approach ensures our estimates reflect the actual market conditions for transaction inclusion. The Wagmi hook returns a nested array structure representing fee history data. Each inner array corresponds to a specific priority level: low, medium, and high. To make this data more accessible and type-safe, we transform it into a structured record. The resulting format is a record where each key is a priority level such as low, medium, or high, and the corresponding value is an array of big int values. This array contains the historical priority fees for that level, making it easier to analyze trend and calculate estimates for each priority tier. To handle the transformation of query results efficiently and safely, we've created a custom hook called useTransformQueryData. This hook is designed to transform raw query data into a more useful format while preserving the query's error handling capabilities. It is particularly useful when working with complex data structure like our fee history, where we need to reshape the data without losing the original query's metadata. The hook uses React's use memo to optimize performance by memoizing the transformed result. To display both historical and current priority fees, we need two data transformations. We first transform the raw fee history into a chart-friendly format, and then we calculate the average of the historical values for each property level to show the current fee. This dual transformation approach gives us both the temporal view needed for the chart and the current snapshot needed for immediate fee estimates. For cases where we only need the fee for a specific priority level, defaulting to medium, the use priority fee query hook provides a streamlined way to access a single priority fee value. This hook builds on top of use priority fees query but extracts just the requested priority levels fee. Having established our query infrastructure for priority fees, let's examine the first component in our implementation: the max priority fee per gas title. This component serves as a section header that dynamically displays the current average priority fee. It leverages the match query component from RisenKit for handling the asynchronous data state, rendering a spinner during loading, and the formatted fee value once available. The next crucial component in our implementation is the priority options, which provides a visual representation of priority fee options. This component displays three priority levels: low, medium, and high, each with its own color indicator and current fee value. To better understand fee trends, we can visualize how priority fees have fluctuated across the last 10 blocks using an interactive chart. The fee chart content component handles the visualization of priority fee trends using our custom chart implementation. This component leverages various utility functions and styled components to create a responsive line chart. It normalizes the fee data arrays, generates appropriate y-axis labels in gray units, and renders three overlapping line charts, one for each priority level: low, medium, and high. Each line chart is color-coded to match the corresponding priority level and indicates a gradient field for better visual distinction. The chart is wrapped in an element size array component to ensure proper responsiveness, and it includes horizontal grid lines for easy value comparison. For a detailed explanation of the chart implementation itself, check the corresponding YouTube video in the description. Now that we understand how to calculate and visualize the priority fee, let's examine another crucial parameter in EVM transaction fees, the max fee per gas. This parameter represents the absolute maximum amount per unit of gas that a user is willing to pay for their transaction. It is calculated at the sum of the max priority fee per gas, which is the tip 2 validators, and the base fee, which is the network's base cost. The max fee per gas component displays this relationship in a clear formula and provides additional context about how this parameter helps manage transaction costs. In EVM-based networks, the base fee is dynamically adjusted by the protocol based on network demand. When blocks are more than 50% full, the base fee increases by up to 12.5% per block, and when they are less than 50% full, it decreases by the same maximum percentage. This mechanism helps regulate network congestion by making transactions more expensive during high demand periods and cheaper during low demand periods. To account for this potential increase between blocks, Web3 applications typically multiply the current base fee by a safety factor. In our implementation, we use a multiplier of 1.125, which matches the maximum possible increase in base fee between blocks. This approach provides a buffer against base fee fluctuations, reducing the likelihood of transaction failures due to insufficient gas fees while the transaction is pending in the mempool. To monitor the current base fee, we've implemented the use base fee query hook that leverages Wagmi's use block hook with the watch option enabled. This setup allows us to continuously track the base fee as new blocks are produced. The hook extracts the base fee per gas value from the latest block data, ensuring we always have access to the most up-to-date network fee information. Since the base fee is an optional parameter in some EVM chains, there should be present utility to handle type safety, ensuring our application only works with the chain that implement EAP 1559 fee mechanism. The base fee component provides users with real-time visibility into the network's current base fee and explains its dynamic nature. Similar to our other fee components, it uses the fee section layout and displays the current base fee value in gray using the match query component for handling loading states. The component includes an informative description that helps users understand how the base fee automatically adjusts based on network demand, making it clear why transaction costs may vary over time. Finally, let's bring all our fee calculations together in the max fee component to provide users with a practical example. This component calculates the total estimated cost for transferring 1 ETH on the Ethereum mainnet. It combines three key pieces of data, namely the current base fee adjusted with our safety multiplier, the priority fee using the medium priority level, and the estimated gas required for the transfer. Using Wagmi's use estimate gas hook, we simulate the transaction to get an accurate gas estimate, while use asset price query fetches the current ETH price to display the fee in USD. The component knew that they use transform queries data to combine these data streams and calculate the total maximum fee, presenting it in both ETH and USD for better user understanding. To provide users with familiar cost references, we fetch the current Ethereum price from CoinGecko using the use asset price query hook. By combining Viem and Wagmi's powerful hooks with real-time data from the Ethereum network, we've created a comprehensive gas fee calculator that helps users make informed decisions about their transaction cost. The application not only provides current fee estimates but also visualizes historical trends and offers different privacy levels to suit various transaction needs. This implementation demonstrates how modern Web3 libraries can be leveraged to create intuitive interfaces for complex blockchain interactions. Don't forget to like and subscribe to the channel.